So let me introduce the first speaker. We have Toby and Clere Smithe, who will give an extended talk, a keynote talk, on cyber kittens or first steps towards categorical cybernetics. So Toby, please, the floor is yours. You can start the screen sharing.
Share my screen, yeah. Okay.
Yeah, there we are.
Great. There we go. Okay, good. An emphasis, I should say, on first steps. I mean, we'll see how this goes, but I'm really a theoretical neuroscientist. So I'm really interested in how neurons composed together generate our intelligent behavior. And I'm interested in the question, how do we construct a system that plays the games that we study in something like open game theory? So I've got this sort of heuristic definition of what I'm going to think of as a cybernetic system. And it's very simple. It's if it perceives and it acts, then it's a cybernetic system. And I think this covers quite a broad class of things that we might think of as cybernetic systems. In particular, it covers things like the brain and brains of different kinds of animals. And also it covers things like machine learning algorithms. Those are the two main classes of thing I'm going to consider. But I think probably systems like corporations and other more social systems probably fall under this kind of definition as well. So the cybernetic systems I have in mind, they don't have access to the important information about the causes of the things they are perceiving, their kind of external state of the world. They have to infer what those causes are, and they have to infer what should be done on the basis of them. And typically they do this inference on the basis of imperfect signals. And this means it's going to be something probabilistic. There are two main features of the brain as a cybernetic system that I'm going to consider today. One is that if you look at the structure of the cortex itself, the circuits of neurons involved have this kind of curious bidirectional structure where you have lots of axons projecting what people call forwards, but also a lot of axons in parallel projecting backwards. And they kind of seem to balance each other in some curious way. And not only do we have this bidirectional structure, but also a lot of people have thought that the cortex and the brain more generally is organized somehow hierarchically. And it looks a bit like a trace model category. If you look in the literature, the diagrams people draw. And it turns out that we can explain both of these features abstractly. So perceiving and acting just mean doing Bayesian inference. And that in turn means embodying a model of the world that will be inverted, some kind of generative model. Then,
excuse me.
Yes?
I'm sorry, technical interruption. Could you please speak a little bit louder?
Oh, of course. Yes. Sorry.
Yeah.
I will. Is that better?
Thank you so much. Yes, thank you.
Okay. So perceiving and acting mean doing Bayesian inference, and that in turn means embodying a model of the world that will be inverted. And we'll see that the inverse of some composite channel, the inverse of these forwards connections, will be composite of the inverses of backwards connections. And that means that the brain can invert each factor of this model locally. And that's how we get this hierarchical structure. And we'll see that this bidirectionality is precisely the lens pattern. So the plan of the talk is that I'm going to briefly introduce categorical probability and Bayesian inversion. We saw a bit of this yesterday in Thomas's talk, so I'm going to only summarize that. Then I'll prove quickly, or sketch the proof, that Bayesian updates compose according to the lens pattern. I will define a class of statistical games using compositional game theory, and that'll cover things like maximum likelihood estimation and Bayesian inference. I'll suggest that cybernetic systems are realizations dynamically of these games, and I'll show some examples of this in variational autoencoders in machine learning and cortical circuits in the brain. And I'll conclude by wondering a bit about interacting systems, nested systems, and things like non-stationary context. Okay, so the basic categorical setting is going to be what has come to be called a Markov category or a copy-delete category. The object of this category is some kind of space, measurable space, or if it's finite, it's just a set. The morphisms will be our stochastic channels, or things that people call conditional probability distribution. So these are like functions from points to beliefs over some other space. States are just going to be probability distributions. These are the channels out in the monoid unit. They're what I'll think of as beliefs. I'm not going to characterize them precisely. I'm just going to think about them abstractly. And then when we compose two channels in a copy-delete category or Markov category, typically we average over the factor, the space in the middle of the composite. And we can do that with this kind of summing over the probabilities here. Important feature of this kind of category is that we can form joint states, beliefs about two things at once, simultaneously, in parallel. And there's this classic rule in probability that says that you can disintegrate a joint state into some prior belief on one factor and a channel or a likelihood or a conditional probability distribution from that factor to some other space. And we get two marginals by throwing away one of the two spaces of the joint space. Using this rule, we can define a kind of abstract Bayes rule, which just says that a channel is the inverse of another channel if you can form the same joint state by composing the prior belief pi here with your stochastic channel C on one side, and then the prior belief C after pi on the right side with your inversion, which I'm going to call C dagger pi. And it's important to note that the Bayesian inverse of a channel, it's not just the inverse function, it's always defined with respect to some prior. So with different prior states, you might have different Bayesian inversions. And the natural question to ask is, what is this thing C dagger? It's not precisely, this dagger isn't precisely a dagger functor on my category of channels, but it can be thought of as a dagger functor. In particular, it takes a map, a prior, and an observation, and it emits what people call a posterior distribution on the other factor of the joint state. And we can think of it like this abstractly. I think of it as a thing called a state-dependent channel. It's a thing that takes in a channel and spits out another channel that it depends on. And we can formalize this using this pseudo functor, this index category from our copy delete category, our Markov category. Here I'm going to assume it's the Kleisy category of some probability monad. And we get on objects this thing stat x. Its identity on objects it just returns the category we started on, but the morphisms are these state-dependent channels. And then on maps, it's effectively defined by pullback. So you get a state-dependent channel in one fiber of this category, of this index category, and you can use a channel C in the base category to pull this state-dependent channel back along it. And we can think of these D dagger morphisms as sort of generalized Bayesian inversions. So given a state pi on the space, we obtain a channel D dagger pi with respect to this prior belief. And then we can pull these generalized inversions back along channels in the base to get new inversions in the domain fiber corresponding of the morphism in the base category. And so the question to ask is, given a composite channel in the base, how do we define the composite Bayesian inversion? Okay, so if our category over which we're defining the category of our Markov category is Cartesian closed, then these index channels from states on A to channels from B to A, they're equivalently just functions that take in a belief on A, an observation in B, and emit a new state on A. And then if you pair this with a channel from B to A, it's just like a simple lens. We heard a bit about these earlier. So that's a map from A to B and a map from A to B back to A, from A and B back to A. And here we've got something a bit similar. It's a stochastic channel from A to beliefs on B, and state-dependent channel from beliefs on A and observations from B back to beliefs on A. And it just turns out that this is a Hom set in the gradient deconstruction of the pointwise opposite of this index category stat. Okay, so this is a bit elaborate, but we don't need to go into an awful lot of detail. It's just the gradient deconstruction, but I've switched the direction of, I've just taken the opposite pointwise of these, in the fibers of this F So objects are pairs of objects in our Markov category and the fiber. And then the Hom sets are, the morphisms are pairs of channels and the state-dependent channels. And then composition just works in the base by composition, and in the fibers by taking your state-dependent channel and pulling it back along the morphism in the base. And so applying this recipe to this functor stat, we get this lens composite of these state-dependent channels, which says that the composite in the fiber is of CDAG and DDAG is CDAG of pi, the inverse of the first channel C with respect to the prior on, say, X, after the inverse of the second channel with respect to pi pushed through the first channel X. So the question that we come to ask is the Bayesian inversion of the composite D after C with respect to the state pi the same as this composite inverse? Okay, and I'm going to prove this graphically. So let's think a bit about the graphical calculus for these things, lenses. And the one I'm going to use corresponds to these categories of optics that we've heard about. Optics are, these days it seems, the contemporary home of compositional game theory. And then we can draw these pretty pictures. These are pictures in the category of Tambara modules. The calculus is due to Guillaume Poisson. And you can compose these lenses, these pairs in the base and in the fiber in this suggested way. So you can see the flow of information much more clearly in these pictures, especially on slides like this. And here we can see that the composition in the fibers in the bottom of these lenses is contravariant, whereas in the base category it's covariant. And that'll be important later. And it turns out that these categories of lenses of state-dependent channels, which I'm going to call Bayesian lenses, they just are optics, and we can prove it like this. We do this weird thing where we embed our Grothendieck lenses of the stat functor into their pre-sheaf and co-pre-sheaf category. We can define a monoidal action like this. I'm not going to go into a lot of detail on this because I don't really have time, but we can define this monoidal action which takes a space M and then returns maps from which generalized, we could think of generalized states on M. So that's the monoidal unit I pushed through this pre-sheaf M. So maps from this object, this set of states into this pre-sheaf. These are natural transformations. And of course, under the Uneda embedding, those just correspond representatively to our state-dependent channels. And then we can do some ninja Cohen calculus to prove that these two definitions coincide. So that these Grothendieck stat lenses are just representable optics of this kind. And then we can vary the second category here if we want, and we can find mixed Bayesian optics, although I'm not really sure what those would be for. Okay, the question now is, does Bayesian inversion commute with lens composition? And we can draw it like this. Is this thing on the left almost equal or equal to this thing on the right? And the answer is yes. And the proof, at least abstractly, is very simple. We just define the Bayesian inverses in this graphical way, as I showed earlier, for C, for D, and then for D after C. And then we just show that the whole thing is equal to this lens composite by defining it like this. So this is the lens composite, and then these are isomorphisms, or really there's sort of almost equalities, but I'm not going to go into detail on that. And just by using the definitions that I gave on the previous slide, we can show that these two things satisfy the definition of Bayesian inversion. And now Bayesian inversions are almost equal. And so these two things are, these two state-dependent channels are the same up to almost equality. And so we can show, so we've showed that the lens composite of these inversions is just the same as the inversion of the composite. So finally, after a bit of this, after all this technical stuff, let's get back to cybernetics. Okay, and we're going to see that inference problems in machine learning and statistics, they are just games in the sense of compositional game theory over Bayesian lenses. So recall that when I started, the cybernetic systems that I'm interested in, I think of them as trying to estimate some kind of external state. So given some complex generative model, they're trying to invert that and form beliefs about the causes of the data they receive, the sense data or something like that. Now, in the wild, a system like this, a cybernetic system, will be trying to improve its estimation. So in game theory, we'll see that there's this notion of a best response, of an equilibrium in classical game theory, but there's no notion of how you compute that in the category. And so it doesn't capture this improvement that I'm interested in. Now, all the interactions of a cybernetic system, they'll be mediated through the boundary of the system. So for instance, that's like your eyes, your skin, your actuators like your muscles. And that's all the system has access to. So it can't access deep into the environment. It has to go always through this boundary. And we'll formalize this notion of boundary with this abstract thing called a context. So these depictions I drew before of lenses, they can be drawn like this on the right-hand side, as more general optics. Just you can box around the copier and the C morphism here and call that C prime. And that's a general optic. And these optics are elements of these Hom objects, these Hom sets on the right, as this is Mario Raman's calculus here. And you could think about the depiction on the left as living inside the tubes on this string diagram on the right if you inflate the tube. So I'm going to do most of my calculations graphically using this calculus. And I'm going to leave behind now these depictions of the individual morphisms and just think about the objects, the sets in which they live. So this object on the right here, this is an object of a set of optics. And given such an object, given such a set of optics, we can define its context to be this thing on the right. It's just something that supplies inputs to the X and B and takes outputs from the Y and A and then does something with them. It doesn't really matter. It's a scalar, effectively, in the category. If the monoidal unit of our category of interest, say our category of stochastic channels, is terminal, which it is in a lot of cases, then this simplifies to this thing here. And if the product is Cartesian, like it is for my Cartesian optics, because I was working in the pre-sheaf category, then we lose this wire on the bottom, and context is just a state on X and a morphism of from Y to B. So that's something that takes the output of the optic and does something with it and feeds it back into the optic. And we just throw, the context just throws away the output of A. Now, we can compose optics with context, and then we get these closed systems. Again, they're just scalars in the category at hand. But a scalar without some kind of dynamic or something, it doesn't really do anything. Maybe it measures a probability, but we're interested in actually witnessing this evolution of the system. Okay, but before we get to that, let's talk a bit about open games, because we now have all the tools to define them. So a game on these pairs of spaces, XA and YB, so it's a game from XA to YB, is constituted by a set of strategies which say roughly how to play the game, and then a play function that takes each strategy in the set to an optic. And then generally, I'm going to forget really about the elements of the strategy set and just work with the optics. And so let's think a bit about what these optics represent in for my systems. So generally, the inputs of type X will be prior beliefs, and in game theory, these are the observations. And then the system will try and produce some kind of predicted outcome, or in game theory, that it produces an action. And these are the elements of the Y space. Then the environment will feed back some kind of actual outcome, or at least in computational game theory, these are utilities. And then the system itself will compute some kind of belief update, and that's what will be output on the A object, in the A terminal here. And in game theory, these are co-utilities, if you're familiar with that. So we've got this play function, and a game also contains this best response function, which takes a context that corresponds to the optic and tells us if I play a particular strategy, whether or not that's a good strategy or whether it's related to better strategies. And so this is a function that takes context and returns relations over strategies. Let's see how that works quickly. So suppose we've got this context, which I'm going to call pi k. Pi will be, for me, a prior belief, and k will be some continuation, some function, some dynamical system that takes outputs from my cybernetic system and then produces new inputs. So there's a new actual outcomes for the cybernetic system. So a best response function here is one that is something that is a function that takes this context, prior belief and a continuation, and says in this world, in this environment, if the system plays this strategy sigma, then it would have done better, it would do better to switch or to somehow improve to this set of strategies, which includes these elements of tau. And these are somehow better. They allow the system to thrive better or perform its task better. The question that I'm interested in is, how do cybernetic systems, how do agents learn this deviation, this strategic improvement? I should say briefly that we can compose these games, and this is quite straightforward because we can compose optics. We take, say we've got these games G and then H, and the strategy is sigma, and then it's big tau. Strategy for the composite game is just a pair of strategies, one from sigma and one from tau, and then we can use both the play functions to figure out how to play the composite game. And then we can define the context of the composite game, and given a context for this composite game down here, we can define local contexts, they're called, for the factors of the composite game. So by just composing the context for the composite with the alternate game, as in this diagram. So given this brief background on making games, this knowledge of this category of Bayesian lenses, we can start to construct some atomic cybernetic systems. So the first one I'll start with is this simple statistical exercise of maximum likelihood. So here we've got a very simple kind of game. It's from a pair of Monod units to a pair of spaces X. And the aim now is to find some state, some belief state pi that best explains the data that's observed through the continuation K. So we think of this as the environment or the machine feeding in some data, and we're trying to figure out the probability distribution which best explains that data. So our play function takes strategies to objects of this type, and these are just states over X. And the context for this kind of game is there's no prior distribution because we're on where our domain here is the Monod unit, but there is a continuation, that's this thing K. And so really the context is just a stochastic channel from X to X, that's this bottom part here. And then a best response for a maximum likelihood game is just finding the distribution which really does best explain the data under the assumption that it's produced by this K channel. Now we can loosen this up, we can generalize this a bit by varying the domain type here to something else. So suppose we've got this simple gain on Z to X. So we can think of this kind of Bayesian inference, this kind of statistical game as performing Bayesian inference. So first of all, we fix a channel in the forwards direction, and we call that channel C. And then the aim of our game is to find a state-dependent channel in the inverse direction, which is closest to the exact inversion of C in the context. So we've got this conditional probability distribution, the stochastic channel C. We've fixed that. The context will give us a prior on Z and a stochastic channel that gives us observations in X. And we want to figure out how to compute the Bayesian posterior distribution over Z. And we can do this quite straightforwardly in this framework. We've got this best response function defined like this. We fixed C, so the only thing that varies is the inversion C prime, and the aim of the game is to minimize the distance between the posterior distribution C prime pi of X for each observation X, and the exact inversion C dagger pi of X given C and the prior pi. And now, because Bayesian updates compose optically, these games are closed under composition. So given two Bayesian inference games, and we can compose them, the composite game is also a Bayesian inference game. Now we can generalize this still further by allowing the forwards channel, the generated model, to vary too. So if we do that, say we fix some subset of channels in the forwards direction and some possible subset of possible inverses in the backwards direction, and we want to do this thing called an auto-encoded game, that is, find a pair of C and C prime such that C after pi, so pi is our prior, so say we take our prior pi and we push it through the channel C. We want to maximize the likelihood of data from K. These are the observations. So we want to be able to best explain the observations we receive given our prior. And we also want to be able to infer the causes of those observations. So that is, find the C prime again that best approximates the exact inverse of C in the context pi and K. And so this is just like a Bayesian inference game, a maximum likelihood game, and a Bayesian inference game. And we can write this down like this. It's really just the same objective. I've just relaxed the requirement that D is a Kullback-Leibler divergence. This kind of objective captures very many models in the machine learning literature. I can talk about that later if we've got time. Now, these games form a monoidal category, particularly in something like the brain. We observe that the system is predicting the sensory data, but also that we can explain action as a kind of prediction as well. So the way people these days think action works is that the brain predicts what the muscle should do, and then the lower level actuators minimize the error in the prediction. That is, they try and find a state, a belief which makes that prediction come true. And so we can talk about action as a Bayesian inference game or an auto-encoded game, and we can talk about perception as an auto-encoded game. And in the brain, we observe that these two things are coupled, so that action beliefs depend on state beliefs, and perception beliefs depend on action beliefs. And at the top of this hierarchy, we have goals, and these are basically high-level predictions about the way the world should be. And at the bottom of the hierarchy, we observe that there are predictions about sense data and predictions about actions, and the whole system is trying to minimize the error in the predictions the whole way up. Okay, so I've given a class of games, maximum likelihood estimation, inference, autoencoders, and they're all of this form. They are optimization games, I call them. So there's some fitness function, phi, which takes a context and strategy and returns a fitness, and how good the response is, the system is. And the question I've been asking along is, how do we improve at performing these kinds of tasks? So the answer I have is that we can categorify these best response relations, make them proof relevant. So instead of just a truth value that says that two strategies are related, if they are related, if one strategy is better than another, we should have a set of trajectories between them. And these are like the dynamical systems which witness the deviation from a worse strategy to a better strategy. And we can characterize this process compositionally using compositional dynamical systems. So we can think of the fitness function as defining some kind of fitness landscape or potential field, and then the system is trying to minimize or maximize its fitness or sort of fall down this potential field. Now, a discrete time dynamical system is a pair of maps. It's an update map, which here will be stochastic. So it takes in an observation and it stochastically updates the internal state. And then there's this deterministic output map. So at each point, so there's the state space S, and it takes inputs in A, and it produces outputs in B. And then the composition of these things, I'm running a short of time, so I'll go a bit quickly. The composition of these things just is to wire outputs, inputs using lens composition, because this is a category of lenses. Just as we defined contexts for our static games before, we can define context for these dynamical games because this is a monolithic category. So we construct lenses over them, and then we can define this thing called the dynamical lens, which is just a pair of coupled dynamical systems. And it's for these dynamical lenses that we can define context. And again, if the nodal units in the underlying category, the nodal unit in the underlying category is terminal, then we get dynamical context given by this object here. And then, because we have these lenses, we can define dynamical games. And they're just open games over dynamical lenses. So strategies here, we can think of them as possible learning algorithms. And so we can have a hierarchy of these games where we're trying to improve not only our performance, but also our method of improving performance. But I won't be able to discuss that today. And so with all these ingredients, we can sort of join the dots together. We can think of this thing called a dynamical realization. So this takes a sort of static game and gives us a dynamical system which plays the game. And on the context, here it will take a static context of belief and give me a constant dynamical system which emits that belief and then performs the function realized by the function of the continuation in the static context. So I'm going to define an open cybernetic system as a static optimization game with a fitness function that factors through some optimization objective, subject to this coherence condition that if we call the state space of the closed system given by the context in the game S, we can project from the state space into the optimization space, and that there is a fixed point of the dynamics, which is also a maximizer of the optimization objective. And I conjecture that I haven't proved these things form a category. And we could classify variational autoencoders as categories of these cybernetic systems.
Toby, sorry.
Yes.
You are out of time now, you realize,
okay.
Yeah, so if you can wrap it up, thanks.
Yes, okay. I won't clearly have time to go into how this works with variational autoencoders. It also works for Carl Friston's free energy framework in neuroscience. And here you get a dynamical system that looks a bit like this wiring diagram. And we see that in the cortex, we get these communications through precision-weighted errors. And we get this bidirectional hierarchical structure. We can think of adjacent layers as local context. And that's it. So we've got Bayesian updates composed optically, inference problems, open games over Bayesian lenses, cybernetic systems, I say, have dynamics governed by this best response function. And then we've got an abstract explanation for the growth structure of cortical circuits. And of course, there's lots of ongoing work. I haven't really talked about continuous dynamics or really truly dynamical games or interaction cybernetic systems. But there's stuff along those lines, and I'm happy to talk about it later. So thank you very much for listening. Sorry, it feels very quick.
Thank you. Okay, so there were a couple of questions posted in the chat. There was one from Todd earlier on. I don't know, Todd, would you like to ask your question, or has it been answered in the meantime? Todd, are you there? Okay,
yeah,
maybe he...
I'm sorry, I'd like to, my question was, what was the base of enrichment V?
Sorry, it's very difficult to hear you.
I think it was, what was the base of enrichment V?
Yes.
Yeah.
Yes, so I'm trying to work fairly generally, but it's just set. So it's basically, I'm going to assume it's a Benabou cosmos. It's complete and co-complete, but we can just think of it as set. And I'm assuming that my measurable spaces are something like quasi-Borel spaces. So the category is Cartesian closed, and I can do all this jumpy around with the Yonnet dilemma without worrying about it. Does that answer your question?
Yeah, that's good.
Okay, thanks. And there was also a question from Alice Cooper. Please go ahead.
Yes, I'm just asking whether there's any neurophysiological evidence that brains perform an equivalent of the diagrammatic calculations that you are exhibiting.
Of the diagrammatic calculations, I'm not sure what that means, but there's certainly a lot of evidence that that cortical circuits like this are actually passing belief updates in this way. And there's also a lot of evidence that the brain has this hierarchical structure, and that the hierarchical structure has this bidirectionality. And so it seems to be very neat that these things are all really very nicely explained and simply explained by these abstract lenses and the cybernetic systems I've tried to sketch.
If I may follow up on that, does back propagation of errors figure into the feedbacks that you are exhibiting? So
here, I tried to talk about these, well, I ran out of time, but I would have talked about these two systems. In variational autoencoders, then yes, I will be doing backprop of error. I'm just doing gradient descent on the strategies effectively. So we actually do get a trajectory over the strategy space. But in the Karl-Friston system, the free energy system for the brain, we're not really doing that. The dynamics is directly on the beliefs themselves. You can think of the beliefs as parameterized by vectors, and then you define a vector field, and these beliefs follow this vector space. But there's no backprop of error in the second system, and there's not so much evidence that the brain is doing that, I think.
Thank you.
Okay. There's another question from, sorry, can I move on? There's a question from Juan Malero. Please go ahead, Juan.
Yeah, hi. I find this all really interesting, and maybe I didn't get something, but I didn't understand the title. Like, why the first bite, cyber kittens?
Cyber kittens. Oh, right. Because Jules Hedges and a few others have started calling categorical cybernetics cybercat, and I like that. And this is kind of preliminary work in that direction. So it hasn't grown up yet, so they're just kittens.
Okay, thanks.
Yeah.
All right, there is one more question. Maybe we can take it very quickly. David, Jazz?
Hi. Thanks. This is great. I'm wondering on your dynamical systems part, what were the morphisms you were using between dynamical systems, or was I misunderstanding what a dynamical system was?
So I'm cheating a bit. My morphisms here just are dynamical systems.
They're lenses.
Yeah, they are just the lenses, and I've defined the HOMs as this dependent sum, and I've kind of wiped away the fact that we know about the states, and we just wire them together.
Okay, so
but
what you
I think this is very crude.
What you call dyne here, I would normally call lenses in the symmetric monodal category.
Yeah. It's basically just smushing together all of the fibers of the discrete dynamic system category in like the sheets of dynamical system paper. I can't remember what it's called.
Okay. Sorry, I think we need to wrap it up to move on to the next talk. Are you? Did it clarify your question, David?
Yeah. So
maybe you can continue offline in the Sulip chat.
Yeah,
maybe. Yeah. All right. Thanks. Let's thank Toby one last time.